This is the third video in a larger series all about power laws and fat tails. In the previous video of the series, we saw how we can fit power law distributions to empirical data. While this can be handy when working with fat-tailed data in the real world, this idea of fat-tailedness is something that goes beyond just a power law distribution. In this video, I'm going to break down 4 ways we can quantify fat tails, and then I'm going to walk through how you can implement these techniques in Python. And if you're new to the channel, welcome. My name is Shah. I make videos about data science and entrepreneurship. And if you enjoyed this content, please consider subscribing. That's a great no-cost way you can support me and the videos that I make. So jumping right into it, in past videos of this series, we've been talking about fat tails, which we defined as when rare events drive the aggregate statistics of a distribution. We saw a salient example of this in the Pareto distribution, where, for example, 80% of sales may come from 20% of your customers. But this idea of fat tails is much more general than any particular distribution. Fat-tailedness is something that lives on a spectrum. Here we have a sort of distribution landscape ranging from thin-tailed distributions all the way to very fat-tailed distributions. We can see the Pareto distributions on the right-hand side here, with increasing level of fat-tailedness. On the far left, we see the Gaussian distribution, which is an exemplar of thin tails or not fat-tailed data. And then we have this middle region, which we saw is populated by the log normal distribution. Taking this view of fat-tailedness as not some binary property of a distribution being fat-tailed or not fat-tailed, but rather a quantity that lives on a spectrum. This naturally begs the question, how do we define fat-tailedness? While there is no true measure of fat-tailedness, there are a handful of heuristics we can use in practice to help us quantify how fat-tailed a given distribution is. And so here I'm going to talk about 4 heuristics, the first being the power law tail index, next being kurtosis, third heuristic is the log normal distribution's sigma value, and the final heuristic uses a metric called kappa, defined by Taleb, whose ideas we talked about in the first video of this series. So starting with heuristic 1, the power law tail index. As we saw in the first video of this series, the smaller a power law's tail index, i.e. alpha, the fatter its tail. This is illustrated by this plot here, where we see with increasing alpha values, you can see the tails of the distribution getting fatter and fatter. So rare events become more and more common as alpha increases. These plots here are generated by this probability density function, where a is just some constant, x is a specific value of a random variable, and alpha is the tail index. So this is the parameter that controls the shape of these tails here. So if a smaller alpha implies a fatter tail, we can naturally use this as a way to quantify fat-tailedness. So in practice, what this might look like is a 2-step process. Step 1 is to fit a power law to your data, and this is exactly what we did in the previous video of the series. And then step 2 is to extract the estimate for alpha. So while this might be a simple approach, it has one obvious limitation, which is if a power law doesn't fit your data well, then this technique is going to break down because the alpha value is essentially meaningless. Another way we can quantify fat-tailedness is via kurtosis, which is a measure of non-Gaussianity. So just taking a step back, the exemplar thin-tailed distribution is the beloved Gaussian, which looks like this. So a Gaussian is thin-tailed because the rare events are so rare they are essentially negligible. For instance, an event that is 5 sigma away from the mean has a 1 in 3.5 million chance of happening, which is in stark contrast to what we see in a Pareto distribution. Taking this as a starting point, the rough idea with heuristic 2 is saying, okay, Gaussians equal thin-tailed, so something that is un-Gaussian or not Gaussian should be fat-tailed. This motivates us to look toward these so-called non-Gaussianity measures, of which kurtosis is the most popular. We can define kurtosis according to this expression here, where mu4 and mu2 are the fourth and second moments of the distribution, which we can define like this. So the intuition with kurtosis is that it will increase as data accumulates in the tail. So more data in the tail means a higher kurtosis. So higher kurtosis means fatter tails. However, there's one major limitation with using kurtosis, namely when talking about Pareto distributions with an alpha value less than or equal to 4, it is not defined. So even if in practice you can always compute a value for kurtosis, when working with very fat-tailed Paretos, those values are meaningless. So heuristic number 3 is using the log normal's sigma value, where the bigger the sigma, the fatter the tail. We got a flavor of the log normal distribution in the past videos of the series, where we saw that the log normal distribution was a bit mischievous because sometimes it could appear more Gaussian-like and other times it could appear more Pareto-like based on this sigma value. An example of this is shown here, where a log normal distribution with mu equal to 0 and sigma equal to 0.2 looks a lot like a Gaussian. However, a log normal distribution with the same mean but sigma equal to 2 looks a lot like a Pareto. Digging a little deeper, this is the probability density function for the log normal distribution. So this equation is what is generating these plots up here. And sigma sits here and here in the expression. And so this is what is driving the shape of this long tail. This observation of bigger sigma implies fatter tails naturally motivates us to try to use sigma as a way to quantify the fat-tailedness of a distribution. So we can do this in a very similar way as we did heuristic 1, where we follow a two-step process. Step 1 is we fit a log normal distribution to our data, and then the second step is to extract the sigma estimate. And this is exactly what we did in the previous video of this series. While again, this is a straightforward procedure, it, like heuristic 1, suffers from the limitation that if the log normal fit doesn't do a good job at explaining your data, then this technique is going to break down. The final heuristic is Taleb's kappa metric. This is probably the most robust of the 3 heuristics we can use. However, it is also the most sophisticated. So I'm going to try to break it down step by step. If you don't really care about the mathematical details, feel free to jump ahead to the example code to see what working with these heuristics in practice looks like. Kappa is defined according to this expression here, where it's a value that sits between 0 and 1, where 0 implies the distribution is maximally thin-tailed and 1 implies the distribution is maximally fat-tailed. And just as a note, this is for unimodal data with finite mean. So there's a lot going on in this expression here, so let's just break it down step by step. First, let's look at these values here, n naught and n. N naught and n are both integers that correspond to 2 samples we can call s sub n naught and s sub n. And so kappa is actually a metric that compares 2 samples together, sn naught and sn, where sn is equal to the sum of n samples drawn from a particular distribution. So for example, if we have a Gaussian distribution, we would just take n samples and then we would sum them all together and that would give us s sub n. Notice these are little s's and this is a big S. These are big s's. And then the simplest example is s sub 1, which you just draw 1 sample from this distribution. If we choose n to be 30 and n not to be 1, we would just plug in 1 and 30 here. We would plug in a 30 here, a 1 here, a 30 here, and a 1 here. But what does this thing mean? Taking a closer look at this term here, m denotes the mean absolute deviation, which is a measure of dispersion around the mean. Breaking down this equation here, this notation is just representing the mean absolute deviation of a particular sample, s sub n, and it's defined as follows. We get the expectation value of the sample, so we compute its mean, then we subtract the mean from each value in the sample, take its absolute value, and then take the average of all these subsequent values. This is broken down a bit more here. E is denoting the expectation value, s sub n is equal to the sum of a bunch of subsamples, and then s sub I is just some subsample of a distribution. The intuition here is that more data in the tail implies a larger mean absolute deviation, because again, it's a measure of dispersion. The more dispersed the data are, the larger the mean absolute deviation. So let's look at a specific example of this. Say we choose n naught to be 1 and n to be 30. In the thin-tailed case, m30 is going to be about equal to m1, so the ratio is going to be about equal to 1. On the other hand, if you're working with fat-tailed data, M30 is going to be much larger than M1, which implies that the ratio is going to be much greater than 1. This is illustrated by these plots here, where on the left, we're seeing how the mean absolute deviation scales with increasing number of subsamples. So on the left, we have the sum of n Gaussians, and on the right, we have the sum of n Paretos. You can see for the sum of Gaussians, the mean absolute deviation goes from about 1 up to about 8. However, when you look at the sum of n Paretos, it starts around 1 and it ends up at around 500. And so with this observation that for thin-tailed data, this ratio is about 1. However, for fat-tailed data, it's going to be much greater than 1. We can see how this influences the kappa metric defined earlier. And so we have our thin-tailed data. This is just plugging in values of n not equals 1 and n equals 30. And so if this ratio is about 1, then this value is going to be very small. That's because the log of 1 is equal to 0. So as the ratio approaches 1, this term will approach 0. So if the denominator is small, that'll make this whole term here big. And then when you subtract it from 2, it's going to make the whole thing small. That's how we can see that 0 implies maximally thin-tailed. However, in the fat-tailed case, we see the exact opposite. So if this ratio is big, then this denominator is going to be big, making this whole term small, and then making this whole term big. That's where 1 implying maximally fat-tailed data comes from. So if this was all way too much math than you were hoping for, here's the key takeaway. Big kappa implies a fat tail, small kappa implies a thin tail. So now let's dive into some example code. Here we're going to quantify the fat-tailedness of data from my social media accounts. This is the same data set we saw in the previous video of the series, and the data set and code are available on the GitHub repo, linked here and in the description below. We'll start by importing some handy modules, namely matplotlib, pandas, numpy, the power law library we saw in the previous video, and then we'll import Kurtosis from the scipy library. Next, we'll load in the data. Again, the data is on the GitHub repo, stored in separate CSV files. What I'm doing here is iteratively reading in each CSV as a pandas data frame, and then I'm storing each data frame into a dictionary. It's always a good idea to look at your data, no matter what data science project you're working on. Here, I'm just looping through each of the different data sets again, so they're all stored in this dictionary, and then I'm just iteratively extracting the data frame, plotting its histogram. So this plot histograms function is a bit long and nothing really special. It just uses matplotlib's hist function. That function's on the GitHub if you're curious, and then the figure's being saved. Another thing that makes sense to look at, since we're trying to evaluate fat tails, here we're going to look at the top 5 records of each data set by percentage. Here are the histograms, so that function actually plots 2 histograms, the histogram of the raw values, and then the histogram of the log of the raw values. This data here are the number of Medium followers gained on a month-to-month basis. Here we have YouTube earnings on a video basis, and then finally here we have daily LinkedIn impressions. Looking at all these histograms, it's pretty clear that they're all fat-tailed to some extent. Medium seems to be the most fat-tailed, and maybe LinkedIn and YouTube are following slowly behind, with LinkedIn being a little less fat-tailed. That's why I like histograms so much. You can extract so much information from just looking at the histogram and a log histogram of any data set. Next, looking at the top 5 records by percentage. Here we can see medium followers is significantly fat-tailed, where 60% of total followers gained is just coming from 2 months. And we see a similar thing with YouTube earnings, where about 50% of earnings are coming from the top 4 videos. However, for LinkedIn impressions, just looking at the top 5, we don't see something as extreme as what we see for medium followers in YouTube earnings. So from this view, we might say that medium followers is the most fat-tailed, YouTube earnings is the next most fat-tailed, and then LinkedIn impressions are the least fat-tailed of the 3. However, let's make this a bit more quantitative by computing each heuristic for all 3 data sets. Starting with heuristic 1, the power law tail index. Here I'm using a for loop just to, again, loop through each of the 3 data sets stored in this dictionary. But the key line of code is just this one line here where we fit a power law to our data. And so this is exactly what we did in the previous video of the series. And then these 7 lines here is just printing the results. And so what that looks like is this, where medium followers, we have an alpha value of 0.8. 0.83. For YouTube earnings, we have an alpha value of 0.9. And then for LinkedIn, we have an alpha value of 1.47. Also note with these fits is that you'll have an X min value. So this fit isn't for the entire distribution. It's starting at some minimum X value, and then the alpha value corresponds to all the values greater than that. The power law tail index matches our intuitions from looking at the top 5 records and from the histograms, where medium followers are the most fat-tailed because they have the smallest alpha, followed by YouTube earnings, and then LinkedIn impressions are the least fat-tailed. Moving on to heuristic 2, kurtosis. We do a very similar thing, but here it's super easy because we can just compute kurtosis in one line of code, and it's already available off the shelf in SciPy. We just load in our data, and then here we're just printing the results basically. Doing some string concatenation here, so kurtosis equals kurtosis of our data, and then Fisher equals true. It's just like a convention to make it such that negative kurtosis values indicate something is even more thin-tailed than a Gaussian distribution, while positive values how more fat-tailed the data are from a Gaussian. The results look like this, with medium followers having a kurtosis of about 21, YouTube earnings 11, and then LinkedIn impressions of 46. This is telling us a different story because the larger the kurtosis implies the fatter the tails. So this is saying that LinkedIn actually has the fattest tail, followed by medium followers and YouTube earnings. One cause for suspicion here is, as we saw in heuristic 1, when we did the power law fit, all 3 data sets had alpha values that were very small, which was below that alpha equals 4 cutoff, for which the kurtosis is not defined for a Pareto distribution. So it's probably wise to take these values with a grain of salt, because if the data truly do follow a power law and the alpha values are as small as we saw in the previous slide, any empirical kurtosis calculation you do is going to be meaningless because the true kurtosis is not defined. Heuristic number 3, this is very similar to heuristic 1. We just load in the data, do the power law fit. It's actually the same exact syntax here. The only difference is that when we print the results, instead of extracting the alpha and X min value from the power law fit, we're extracting the mu and sigma value from the log normal fit. And so that's one cool thing about this power law library. When using this fit method, it'll automatically estimate the power law distribution parameters and the log normal distribution parameters. The results look like this, where medium followers has a sigma of 2.4, YouTube earnings 5.4, and then LinkedIn impressions 2.3. And so we're again seeing another story here where, since the larger the sigma, the fatter the tail, here YouTube earnings is the most fat-tailed, followed by medium followers and then LinkedIn impressions. However, something that stands out to me is that the mu value here is negative, which might tell me that this log normal fit may not do a good job at explaining the data. And as we mentioned previously, one of the limitations of heuristic 1 and heuristic 3 is that if the power law or log normal fit doesn't do a good job at explaining the data, then these approaches tend to break down. Moving on to heuristic number 4, since I couldn't find an off-the-shelf implementation of this metric, this is going to take a few more steps. First, we need to implement the mean absolute deviation. Again, this is the expression we saw before, and then this is what it looks like in code. Next, we need to generate n samples from our data set. In practice, you don't have like a true distribution which you can sample so readily. Often you just have a set of values. You just have an array of numbers, and we need to somehow generate samples from that empirical data to do the kappa calculation. Recalling the definition of SN as you just take a bunch of samples from some underlying distribution and sum them together, all I'm doing in this code here is, instead of sampling from some true distribution, I just sample from the empirical data set. This is probably a bit naive, and I'm sure there's some issues with it, but this will be sufficient for our purposes here. What this looks like is just initializing SN to be 0, and then taking a random sample from our data X, so X is just some array of values, take a random sample from it with the same size. This is a very verbose way of doing it, and it's just an artifact that I was playing around with different sizes of samples, but ended up just using the same length as X. And then this just recursively adds to itself until we reach n number of samples. With the mean absolute deviation defined and a way to generate samples defined, we can implement kappa. This function is restricted to kappa values with n not equal to 1, and we'll just set that equal to the data that we're working with. with, and then SN will be generated from that function we defined in the previous slide. Then we'll compute the mean absolute deviation for both of these samples, and then we'll compute kappa in just one line of code. Now, using this definition of kappa, we can compute the metric in a similar way as we did the other heuristics. We need to define the number of samples in the kappa calculation. So we're going to compare S100 to S1. So we're just going to grab each data set, and then we're going to compute kappa in one line of code here. So the results look like this, where medium followers have a kappa value of 0.27, YouTube earnings 0.39, and LinkedIn impressions 0.31. While this might seem to tell us a different story as we've seen with the other heuristics, given the implicit randomness in the kappa definition, namely when we defined S100, we're randomly sampling our empirical data 100 times. So if you run that calculation 3 times, you're going to get 3 different kappa values. So instead of just running this calculation once and drawing conclusions from it, it's a better idea to run this calculation many times before drawing your conclusion. That's what I do here. So I just set number of runs equal to 1000. I just define some kappa dictionary to store kappa values for each data set. Here I'm just grabbing one of the data sets. I initialize a kappa list because we're going to run this calculation 1000 times, and every time we run it, we'll just append the kappa value to this list. Here's where we actually do the kappa calculation. So this loops 1000 times, and then this list will store it in the kappa dictionary with a key equal to the file name of that data set. And then we just do this 3 times for each of the data sets. The results look like this. And so again, when you run this calculation, you're going to get all sorts of different values for kappa, but it'll start to look like a Gaussian as you do more and more runs. So the mean is a representative value of this distribution. Here we see the mean kappa for medium followers is about 0.4, for YouTube earnings it's about 0.3, and for LinkedIn impressions it's about 0.34. The story we're getting here is that medium followers is the most fat-tailed because, again, the larger the kappa, the fatter the tail, followed by LinkedIn impressions, and then followed by YouTube earnings. Based on all these heuristics and looking at the plots and stuff, it's pretty clear that medium followers is the most fat-tailed of the 3 distributions, with YouTube earnings and LinkedIn impressions being kind of debatable which of the 2 is more fat-tailed. So if you want to dig a bit more into this topic, check out the blog published in Towards Data Science. Even though this is a member-only story, you'll be able to access the article completely for free, even if you're not a Medium member, using the friend link in the description below. And this is the case for any video and blog combo that I make. Also, check out the GitHub to get access to the datasets I looked at here, as well as the example code. And if you enjoyed this content, please consider subscribing and sharing with others. That's a great no-cost way to support me and all the videos that I put out. And as always, thank you so much for your time, and thanks for watching.